At Fermilab, we study nature at its most fundamental, drilling down to the smallest scales of matter using some of the largest and most advanced machines in the world. Accelerators, powerful microscopes, send particles barreling at near light speed into other matter, creating subatomic scraps. Detectors zoom in on those fleeting pieces, making the invisible perceptible. And sophisticated computers sweep through all of it, crushing mountains of information into gems of data. We also use our cutting-edge technology to explore the mysteries of dark matter and the quantum realm. Thousands of scientists from around the world partner with Fermilab to explore how the universe works, expanding humanity's understanding of matter, energy, space, and time. Fermilab is solving the mysteries of the universe.
Today's presentation is Sources of Radiation from Outer Space, Gamma Rays of Doom and Destruction. I am Rick Polad. I'm an education facilitator at Fermilab, and I will be moderating today's event. Please type any questions you have into the chat, and we'll answer those after the presentation. Following the questions, we'll show a short drone flyover of the Fermilab campus. It is now my pleasure to introduce Dr. Jim Welsh. Jim is Chief of Radiation Oncology at the Edward Hines VA Medical Center and Professor and Director of Translational Research at Loyola University's Stritch School of Medicine. He is past president of the American College of Radiation Oncology and editor-in-chief of the Journal of Radiation Oncology. He has spoken at Fermilab in the past for our Ask a Scientist program and the colloquium. He is currently involved in research on the use of low-dose radiation to treat the cytokine storm associated with COVID-19 pneumonia. And he is the author of Sharks Get Cancer, Mole Rats Don't: How Animals Might Hold the Key to Cancer Immunity. Good afternoon, Jim. It's all yours.
Okay, thanks, Rick. Well, it's a pleasure to be here with everybody today, and welcome to Ask a Scientist. I'm sorry that it's not in person, but that day is coming soon. And I wore my Fermilab tie here today to provide a modicum of credibility and to make it as official as possible. So with no further ado, let's see if I can share my screen and get the show started here. Can you see it yet? All right. So today I'll be talking about what I hope is a very interesting subject: radiation from outer space, gamma rays of death, doom, and destruction. Various sources of high energy radiation are out there. And so what I'll talk about today are a variety of topics, including serious solar flares, cosmic rays from hell, strange circumstances that might strengthen the impact of cosmic rays on our biosphere, gamma rays of death, doom, and destruction as advertised, the birth and death of black holes, which confer large amounts of radiation to the local environment, and other exotic sources of radiation from outer space. Finally, we'll stop with how bad is it all going to be, really? So, with no further ado, let's talk about the Carrington Event. And this was an event, 1859, where we didn't have telephones, televisions, modern electronics, but telegraphs were in vogue at the time. And the telegraph wires, pylons, overheated. They were electrically induced. They got fried, basically. They caused electric shocks in the telegraph operators, set fires, and really closed down the grid of that time. Additionally, auroras were seen around the world, as far south as the Caribbean and Mexico. Gold miners in the Southwest woke up because of the skylight and started brewing their coffee around midnight. started reading the paper, assuming that dawn was breaking. But it wasn't dawn. It was caused by a monstrous solar flare, or maybe a coronal mass ejection that happened to be headed right our way. This is an example of a solar storm. And solar storms are an example of solar weather. If this happened today, what would happen? Well, with our dependency on computers, for example, with this Zoom meeting we're doing, cell phones, televisions, other electronics, the entire electrical power grid is at risk because we're more dependent, our system is more sensitive, and we're far more vulnerable than ever before. Additionally, these kinds of events can occur about once per century. So have we just been lucky, or are we past due? What would happen? Yeah, it could be like that. It could be a disaster. And so let's talk about the weather, the solar weather, that is. The solar wind is always out there, although it's not always the same strength. There are solar prominences, solar flares, coronal mass ejections, other forms of space weather that abound. Here's a solar prominence, which happens to be a relatively minor solar eruption, relatively gentle. On the other hand, solar flares can be quite energetic and release large amounts of radiation, as can coronal mass ejections, which blast off large amounts of plasma and electromagnetic radiation into space, sometimes headed our way. These can be associated with solar flares and are often quite dramatic. As you can see, solar coronal mass ejections can be as large as the sun itself. And if headed our way, that could be an interesting day. So we say that the sun emits X-rays. Why is that? Well, when you think about it, we say that the sun's surface temperature is 5,800 Kelvin, let's call it 6,000 Kelvin. Most of the electromagnetic radiation at that temperature should be in the optical range, visible light. 6,000 Kelvin star should be an extremely weak source of X-rays. Yet the sun is a strong X-ray emitter. Why is that? Well, if you remember your black body radiation physics with Planck curves, Planck formula, the Wien's law, etc., you could see at 6,000 Kelvin, there really shouldn't be much X-rays, but there are. So where are they coming from? The answer is they're coming from the solar corona, not the photosphere, the surface of the sun, but rather from the sun's atmosphere, the outermost layer. The outermost layer of the sun's atmosphere, the corona, can be extremely hot, 1 million degrees, maybe 2 million degrees, and it certainly can emit X-rays. So we talked about solar weather in the form of solar wind, solar prominences, flares, coronal mass ejections. These are all more prominent during solar max, or solar maximum. What does that mean? Well, solar maximum simply alludes to the time during which sunspots are most prevalent. And if you recall, sunspots are due to tangling and snapping of magnetic lines of force as they bubble up through the convection zone towards the photosphere. And when they snap, they might release energy into the corona, giving it its 1 million degree temperature. But this is one of the most interesting puzzles in all of solar physics. It's still not sure, we're still not sure exactly how the corona is so hot. But we do know that sunspots follow a cycle. So that here's a close-up of a sunspot. Although it looks dark and cool, don't be fooled. It's plenty hot. It's not quite as hot as the 6,000 degree photosphere around it, but couple thousand degrees cooler is still hot enough to cause some trouble. But sunspots come in cycles, and every 11 years or so, we reach a maximum in that cycle, the so-called solar maximum. This is the Schwab cycle, or the sunspot cycle, in which every 11 years we have a maximum of sunspots. Interestingly, during this time, the sun's north pole and south pole have switched places, so that north pole becomes south pole every 11 years, and then every 22 years you go through the so-called full hail cycle of north pole going to south pole and back to north pole again. Then there are various other cycles associated with sunspots that reflect the waxing and waning of the amplitude of the number of sunspots over 88 years, 200 years, 2,400 years, etc. One phenomenon that's of great interest is the grand solar minima phenomena. An example of this is the Maunder minimum. I think 1645 to 1715 or so, there were very few, if any, sunspots spotted. And it wasn't for lack of looking, because the telescope was invented in that century and people were avid viewers of all things cosmic, but no sunspots were seen. And coincidentally, the little ice age was upon Europe and North America. Was there a connection? Very interesting possibility. I'll talk a little bit about other grand solar minima that occurred after the Maunder minimum, such as the Dalton minimum, which was documented by sunspot count, but others were not directly detected through sunspot count, but rather through proxies that I'll talk about in a minute. So, is there a real connection to the Little Ice Age? What could the connection be, and what would the mechanism be all about? Well, if you think about the insolation, the amount of radiation in terms of watts that we get here on the Earth's surface during solar max versus solar minimum, it's much less than 1%, in fact, less than 0.1%. So can that really affect our climate? Probably not. But here's something interesting. The decreased solar wind decreases the deflection of galactic cosmic rays. So during a grand solar minimum, increased galactic cosmic rays come our way. What are galactic cosmic rays and where do they come from? Well, exactly where they come from remains a mystery. It's believed that they come from supernova, some form or fashion, and they come blazing in towards our solar system at nearly the speed of light, extremely energetic stuff. Cosmic rays can be divided into primary cosmic rays and secondary cosmic rays, depending on their composition and where they've come from. So primary cosmic rays are protons, helium nuclei or alpha particles, and heavy atomic nuclei all the way up to uranium. These are sometimes called HZEs, high Z for atomic number and high E or energy. Secondary cosmic rays occur when the primary cosmic ray strikes the atmosphere, as in this illustration. The secondary cosmic rays are caused when the primary cosmic ray blasts into the atmosphere and causes a shower of secondary radiation. Secondary radiation such as pions and muons and other particles, including neutrons, which I'll talk about in a bit because neutrons are what produce carbon-14. So here are some secondary cosmic rays coming down in a shower. Here's a video that shows what's happening all the time. These secondary cosmic rays are raining out of the sky on a regular basis, more so during the near the North Pole and the South Pole than towards the equator, but everywhere is affected. So I mentioned that not all solar minima are documented directly by sunspot counts. For example, the Spora, the Oort, the Wolf minima were all they all took place before the invention of the telescope in the 17th century. So they were not documented by sunspot observation. They were documented by proxies. Proxies or surrogates such as carbon-14, beryllium-10, and other cosmogenic radionuclides. Carbon-14 might accumulate in tree rings, for instance, and we could correlate the amount of carbon-14 with the weather at that particular time to see if there is any kind of correlation at all. So cosmogenic nuclides are surrogates for grand solar minima, but are they good surrogates for past climates? It's a good question. What are good surrogates for past climates? We're now dealing with the subject of paleoclimatology. And in paleoclimatology, we know about dendroclimatology. This is the examination of tree rings. And tree rings allow us to go back hundreds of years, or maybe even 1,000 years, by overlapping tree rings from long dead wood samples. Polar ice from glaciers can go back thousands of years, maybe hundreds of thousands of years, or perhaps even a couple of million years. Calcareous marine fossils, like corals and clams, can allow us to extrapolate the climate from millions of years ago. So, as you might imagine, tree rings can reveal a lot about the climate and weather at the time that the tree was growing up. So thinner annual tree rings might reflect years of lower rainfall, and thicker ones might indicate a more conducive climate. And you can go back and look at these tree rings going back many hundreds of years. For example, in this very large tree that's got many tree rings, you can see documentation of the 16th century mega drought in the area that this particular tree grew up. And in a similar fashion, glacial ice cores can go down many meters, hundreds of meters deep into the glacier and provide samples of snow from many years ago, perhaps thousands of years ago. And what they do when examining these ice cores is not look at carbon-14 so much, but look at maybe some beryllium-10, but also heavy isotopes of hydrogen and oxygen. Heavy hydrogen is called deuterium, and oxygen, if you recall, comes in two forms, oxygen-16 and the heavier isotope oxygen-18. In any case, when the climate is warmer, it means that more of the heavy hydrogen and oxygen can get tucked away and sequestered in glaciers. Conversely, when the ocean is warm, I gotta have it backwards here. When the climate is warm, you can have isotopically heavy oceans, and when the climate is cold, the oceans get isotopically light because the deuterium and heavy oxygen are sequestered on the glaciers. Same thing can be documented through corals. Calcium carbonate is what corals are made out of. And the oxygen 18 in this CaCO3 can tell us something about the climate that the corals grew up in, whether it was recently, thousands of years ago, or millions of years ago. So proxies can tell us about past climates. But just how reliable are cosmogenic radionuclides like beryllium and carbon-14? That's debated. But where do they come from? One explanation is that they come from supernova explosions. And Crab Nebula here is a classic example of a supernova. It was first observed by Chinese astronomers in the year 1054, documented by them, and it's a probable source of galactic cosmic rays. How do they form? Well, many of them form in a binary system with red giants and white dwarfs. Here's an example of a white dwarf being fed material from a giant, red giant, and going off as a type 1a supernova. And when it does so, notice that there is no white dwarf left behind. There is no remnant, no black hole, no neutron star, no white dwarf. It's blasted to smithereens as far as we know. But supernova can be as bright as an entire galaxy, and they may be the source of cosmic rays. So cosmic rays come raining down out of the sky, and they smack into our atmosphere and form secondary cosmic rays. Secondary cosmic rays can include neutrons, which interact with nitrogen 14 in our atmosphere, and then create the carbon-14. For those of you who like the full equation, here is the decay of the carbon-14 through beta decay and the emission of an anti-neutrino. It occurs with a half-life of about 5,730 years. Well, carbon-14, the radioactive carbon-14, then becomes radioactive carbon dioxide. This radioactive carbon dioxide gets into the food chain. It's taken up by plants for photosynthesis, which means that all plants are radioactive. And since animals eat radioactive plants, they become radioactive themselves, which tells us that all animals are radioactive as well. Upon death of the animal or the plant, it can no longer take up the radiocarbon. And from that point on, the carbon-14 decays away, and you can measure the ratio of the carbon-14 to carbon-12 in a sample and get an estimate of how long ago that animal lived and died. Muons are other examples of cosmic rays, secondary cosmic rays. They come from pions that are produced in the upper atmosphere, which rapidly decay and generate these muons. Muons can strike the surface. Muons should only live about 2.2 microseconds, which means that they shouldn't make it to the Earth's surface if they're made many kilometers above the surface here in our atmosphere. Yet on the surface at sea level, approximately 10,000 muons pass through our body every minute. So this is a classic example of special relativity, prolonging the perceived lifetime of these muons and allowing them to reach our surface and strike us. They penetrate through the entire atmosphere, going from through the exosphere, thermosphere, and all the way down through the troposphere, which is 80% of our atmosphere, and striking us here on the surface. So this raises the atmospheric radiation paradox. Our atmosphere generates more radiation by multiplying primary cosmic rays into secondary cosmic rays. But the atmosphere presents an excellent barrier against electromagnetic, uncharged radiation, gamma rays and X-rays. So talked about particle radiation in the form of cosmic rays. Well, they are electrically charged. And if the atmosphere cannot attenuate these electrically charged energetic particles, what can? Well, maybe geomagnetism can come to our rescue. We can depict the Earth's magnetic field as a bar magnet, and that provides a geomagnetic shield. This geomagnetic shield can help protect us by deflecting electrically charged particles. It doesn't protect us from electromagnetic radiation. So photons can penetrate the geomagnetic shield, but they don't penetrate the atmosphere. So these charged particles follow the electric lines of force, the magnetic lines of force, and form the Van Allen belts, which are configured in an inner belt and outer belt for the most part. The outer belt is where electrons accumulate, and the inner belt is where protons accumulate, somewhat akin to an atom with the electrons orbiting the positively charged nucleus. They are arranged in the form of two giant donuts or bagels of radiation surrounding the Earth. And recently, the Van Allen probes discovered that maybe a third belt transiently exists. The charged particles bounce back and forth between the north and south poles, following these helical patterns along the magnetic lines of force. And one of the very interesting things is possibility of antiprotons in the Van Allen belts. When primary cosmic rays with their high energy smash into atmospheric molecules, they create a shower of exotic particles. Among those exotic particles are antiprotons. Very cool. Another thing that's very cool, or at least I thought it was when I was a kid, was this movie, Voyage to the Bottom of the Sea. What are they looking at up here? Well, they're looking at the sky. And the sky is a bright red here. Why? Well, yep, you got it. The Van Allen belt caught fire. And the Van Allen belt is about to explode. And people of Earth have to flee a rain of fire coming from the sky. Sounds absolutely ridiculous, doesn't it? How could it be? One of my favorite movies is just so full of it's nonsense, right? Wrong. It might be true. Very recently discovered was the idea of electron rain coming out of the sky thanks to lightning, which produces so-called Whistler waves. Whistler waves are an example of very low frequency radio waves. Along with chorus waves, Whistler waves propagate through the ionosphere. They interact with the electrons in the Van Allen belts. And when the Whistlers interact with the electrons in the Van Allen belts, electron rain comes pouring out of the sky and strikes our atmosphere in the polar regions. It could contribute to the auroras, making them more intense and beautiful, but it could pose some hazards to satellites, spacecrafts, and astronauts. So here's a diagram of the Whistler waves originating from the lightning, which then get into the ionosphere, interact with the electrons in the outer Van Allen belts, and cause the electrons to come raining down out of the sky in the polar regions. Interesting. So here again is our atmosphere, which serves as a protective cocoon. And it therefore shields us from electromagnetic radiation. Gamma rays and X-rays cannot get through this shield. And particulate radiation is also largely blocked. But then that begs the question, how stable is our atmosphere? Is it going to be here forever to protect us? Is our atmosphere vulnerable to radiation? What would happen if a gamma ray burst directly hit us? Well, if it is a direct hit, we could be in for a very bad day indeed. So what does radiation do to matter in the first place? There are several means through which gamma rays interact with matter. You probably have heard of Rayleigh and Thomson scattering, which doesn't deposit dose, but the photoelectric effect and Compton effect certainly do directly deposit dose. And if the radiation is energetic enough, pair production and photonuclear disintegration reactions can occur. Interestingly, I submit that radiation is the most powerful oxidizing agent of all as well. So after all, it's called ionizing radiation, which implies that it can tear electrons off atoms and molecules and create ions out of them. Well, chemical oxidizers remove electrons from molecules, including biological molecules like DNA and enzymes, and oxygen peroxide, ozone, Clorox, hypochlorite, fluorine. They're very powerful oxidizing agents. They're powerful for chemical agents, but how about physical agents? I think a bare iron 56 nucleus with 26 unshielded positively charged protons ripping through matter would put even fluorine to shame. What about a positron to remove electrons? How about you just disintegrate the electron altogether through neutral annihilation? That's one way to get rid of electrons for sure. Well, let's return to gamma ray bursts. Gamma ray bursts come in two flavors: long duration gamma ray bursts and short duration gamma ray bursts. Both of them lead to a black hole. So they represent the birth cries of black holes. The long gamma ray bursts are thought to be caused by the collapse of a hypergiant, very large star that might end in a hypernova. The hypergiant stars are millions of times more luminous than our sun, but they have lifespans far, far shorter, maybe just a few million years compared to our 10 billion year lifespan for our sun. On the other hand, the short duration gamma ray bursts are associated with the merger of two neutron stars in something called a kilonova blast. So, starting with the death of a giant, a hypergiant might undergo a collapse. This collapse is called the collapsar. It leads to the formation of a black hole. At the end of their short lives, some, but not all hypergiant stars, may end their lives in a hypernova explosion, a king-sized supernova, maybe 10 or 100 times more energetic than a typical supernova. We're talking about something like 10 to the 45th joules. In any case, it emits jets of plasma at nearly the speed of light from the rotational axis. And these are the origins of the long, soft gamma ray bursts. So here's a depiction of a superluminous supernova, a hypernova, and these are sometimes associated with collapsars, which can sometimes produce these long duration gamma ray bursts. So when these plasma jets are firing out of the poles, they interact with one another, they interact with the interstellar medium and generate these gamma rays that could be headed our way. The other type of gamma ray burst comes into existence through the clash of two heavyweights, such as two neutron stars orbiting each other, or maybe a neutron star orbiting a black hole. In any case, these heavyweights circling each other lead to ripples in the fabric of space-time, and they produce gravitational waves. The gravitational waves draw off energy, and the two neutron stars might draw in closer and closer to each other. They eventually will collide and lead to the birth of a black hole, or a bigger black hole if the black hole ate the neutron star that was orbiting it. In any case, a kilonova explosion can occur here. And similarly, this leads to jets of plasma traveling at nearly the speed of light, and these jets will generate the short, hard gamma ray bursts. Here's a video showing how two neutron stars might orbit and collide and lead to short duration gamma ray bursts. Both the short and long duration gamma ray bursts share the same mechanism through which the gamma rays are produced. That is the so-called fireball model. And that's where the plasma comes blasting out of the poles, smacks into each other. The plasma blasts blobs smacking into each other and smacking into the interstellar medium to produce gamma rays and afterglows, which might be in X-rays, visible light, and other electromagnetic radiation. So why does this occur? How does this produce gamma rays? Well, any charged particle that undergoes an acceleration generates photons. High energy electrons, for instance, in an X-ray tube or a linear accelerator will strike a tungsten target and suddenly stop. They decelerate. This is how medical equipment generates X-rays for diagnostic radiology or cancer therapy. Similarly, plasma particles are traveling close to the speed of light. When the plasma decelerates upon smacking into other blobs of plasma or the interstellar medium, the result is that gamma rays and X-rays are spawned. So here are some depictions of gamma ray bursts, and if you're on the receiving end of one of these beams, could be a bad day. So what would happen? What kind of damage might a head-on hit induce? Well, thanks to the thickness of our atmosphere, gamma rays probably would not reach the surface. Nevertheless, the atmosphere itself may take a beating. The atmosphere could be ruined. How? Well, gamma rays are powerful oxidizing agents, and it's 78% molecular nitrogen. The gamma rays could oxidize the molecular nitrogen, producing free radicals and reactive nitrogen species. These chemical entities, the free radicals, could destroy our ozone layer. Remember, the ozone layer is in the lower stratosphere, and it blocks out essentially all of the UVC, most of the bad UVB, and filters out a good fraction of the UVA too. Ozone is interesting because there's a paradox. Ozone is critical for our biosphere. It's essential to us because it protects us from the damaging high energy ultraviolet light. Yet ozone itself is produced by light. Although we talk about, lightning can produce ozone down here in the troposphere at sea level, and it's a pollution, it's a problem for those with asthma, etc. The protective ozone layer that I'm talking about is many miles up in the lower stratosphere, and it's a product of photosynthesis, a photochemical product of the oxygen produced by photosynthesis. Well, let's take a step back and look at some of these mass extinctions from the distant past. There were 5 big ones, including the Ordovician extinction, which occurred about 440 million years ago. 85% of all marine life was wiped out. Remember, there were no land creatures at that time. And The Ordovician ended relatively suddenly with the mass extinction. And this was interesting because it was during a period of major proliferation of life forms. It's called the biological or evolutionary adaptive radiation, a burgeoning of biology. Adaptive radiation is another interesting use of the term, but it's also called divergent evolution. In any case, the Ordovician adaptive radiation was almost as spectacular as the Cambrian explosion was. Nevertheless, it was cut short by the mass extinction at the end 440 million years ago. How did it happen? Most paleontologists attribute it to climate change and tectonic activity leading to continents moving over the poles and affecting our climate that way. But some have proposed that a gamma ray burst could have been a cause and oxidized the atmosphere, destroyed our sensitive protective ozone layer, and the gamma ray burst, interestingly, could also explain the onset of glaciation because nitrogen dioxide produced through the oxidation of nitrogen is a dark colored aerosol. It's a smog, blocks out the sunlight, cooling the earth, and perhaps precipitating an ice age. In any case, ozone depletion could be a problem. Remember, in the Ordovician, there were no land animals yet. All right, everything's living in the ocean, right? But trilobites are benthic. At least adult trilobites were benthic, meaning they were bottom feeders, bottom dwellers. They had a substantial layer of water above them to protect them from the ultraviolet. But modern arthropods have a larval phase that is planktonic, floating at the surface. Probably trilobites had the same kind of planktonic larval stage that was vulnerable to the ultraviolet at the surface. And these planktonic life forms, planktonic larvae, as well as the phytoplankton, could have been fried by the unscreened ultraviolet. So here are some dioramas and illustrations of various creatures that might have abounded in the Ordovician seas. You can see some of these trilobites on the bottom and these interesting orthocone nautiloid cephalopods, the top predator at the time. Sorry about this Silurian sea scorpion. I know it's an anachronism for those of you who are paleontology buffs, but did it really happen? I don't know. Unlike the KPG or KT extinction that led to the demise of the dinosaurs, there was no smoking gun like an iridium anomaly or a crater or a cenotes that provided the unequivocal proof. So whether or not it was a gamma ray burst, who knows? But if it did happen, could it happen again? Well, this is an interesting thing to speculate. Are there any potential hypernova in our vicinity? There might be. This Wolf-Rayet star is about 6,000 light years away, maybe 8,000 light years away, and it might be aimed our way. Most astronomers say that it's off by maybe 30, 40 degrees. Used to be believed that this star was headed right towards us. Probably not. But it is in Sagittarius, the Archer, which begs the question of just how good his aim is. So we say, he's not going to hit us. He might say that's bull and hit a bull's eye. Who knows? So gamma ray bursts represent the birth of a black hole. The birth of a black hole somewhere might have been linked to death of a lot of life on Earth at the end of the Ordovician period. What about the death of a black hole itself? Could the death of a black hole cause death here on Earth? Well, if you recall the Hawking radiation, which is named after Stephen Hawking, one of the greatest scientific minds of all time, and his discovery of the concept of Hawking radiation is, in my opinion, his most valuable, ingenious contribution to all of science. He came up with the idea that black holes could evaporate, and they evaporate by giving off radiation slowly but surely and steadily. And his explanation was that there are particle pairs at the event horizon. If you recall, virtual particles come in and out of the vacuum in this seething froth of the vacuum, and particle pairs might come into existence from this vacuum, and one member of the pair, an electron or a positron, falls into the black hole while the other one remains outside, and this leads to slow evaporation of the black hole. After all, you're kind of creating a particle out of vacuum, and particle means that you've created energy. If the energy is leaving the vicinity of the black hole, means that the mass must be leaving the vicinity of the black hole, and it would slowly evaporate. Interesting idea. And what it means is that as time goes on, the Hawking radiation rate will pick up as the black hole gets smaller and smaller. The black hole gets starts to evaporate, and in the end, it disappears and goes out with a bang. But let's not go worry about this, because these black holes aren't going anywhere anytime soon, especially larger ones. You could look at the equations on the bottom for black hole temperature and time for evaporation. You'll see that a black hole, the mass of the sun, would take about 10 to the 67th years to evaporate. The one at the center of our Milky Way might take 10 to the 87th years, and some of the supermassive black holes could take a googol years, 10 to the 100th power, to evaporate. And for some of the more knowledgeable physicists in the audience, I know that the explanation of Hawking radiation here is not considered accurate or adequate, because a better explanation might have to do with the Unruh radiation, wherein accelerating reference frames see radiation in the vacuum of space. Well, if that's true, what is a gravitational field? It's akin to an accelerating reference frame. And so instead of seeing Unruh radiation near the event horizon, you might see the Hawking radiation. It's complicated, and don't have time to do it justice here. But we will talk a little bit about another form of gamma radiation from the sky in the form of soft gamma radiation, soft gamma repeaters. These are examples of neutron stars. Neutron stars come in several forms, including pulsars and magnetars. Pulsars are kind of like a flash, the lighthouse, and you only see them when the beam is directed right at us. Some of these neutron stars, including pulsars, can have extremely powerful magnetic fields. So you can be this so-called magnetar as well as a pulsar. Magnetars are very interesting because they probably explain soft gamma repeaters. This is probably the basis for the magnetar model. They're incredibly powerful magnetic fields with maybe 10 to the 11th Tesla. Remember, powerful MRI machines, which can really cause stuff to move across a room, are only 3 Tesla. Well, anyway, these magnetars can undergo starquakes. And starquakes occur when the crust of a neutron star suddenly undergoes readjustment, maybe because of the intense magnetic field underlying the crust. This is believed to be the mechanism behind soft gamma repeaters. So when these magnetars have starquakes, a lot of energy is released suddenly, leading to the soft gamma repeater outburst. So soft gamma repeaters are another astrophysical phenomenon that lead to bursts of gamma rays, but they aren't gamma ray bursts. That's a term for a different entity. The soft gamma repeaters are usually producing X-rays, but every once in a while they can crank out some heavy duty radiation up to 10 MeV. That's some hard liquor. That's a powerful gamma ray, and it's no longer in the soft gamma ray category. But the bottom line is that these soft gamma repeaters produce the most intense cosmic ray fluxes on Earth. So let's talk a little bit about X-ray, gamma ray astronomy. Here's a supernova remnant seen by the Spitzer, Hubble, and Chandra telescopes, with Chandra showing the X-ray radiation. Here's the Crab Nebula with the blue core in the middle being the X-ray radiation. X-rays also emanate from white dwarfs because they're so hot and they cause the gas around planetary nebula to glow in the visible light. Planetary nebula are the remnants of red giant star that blew off its outer layers near the end of its life, leaving behind a white dwarf in the center. And that white dwarf gives off ultraviolet and X-ray radiation that causes the cloud to glow. This is the so-called hourglass nebula. To me, it doesn't look like an hourglass. It looks like some kind of creepy creature with a big eye staring right at me. It reminds me of these deep sea creatures like this sea cucumber. In any case, undoubtedly, planetary nebula are among the most beautiful entities in all of astronomy. And they fluoresce for the same reason that scorpions fluoresce. You might remember from basic physics through these Jablonski diagrams that high energy radiation in the form of ultraviolet in the scorpion or X-rays in the white dwarf lead to de-excitation and emission of visible light that we see. So X-ray pulsars are another category of source of X-rays from outer space. One type of X-ray pulsar is due to young neutron stars that are hot, millions of degrees maybe, and perhaps the poles are so hot that they're emitting thermal or black body X-rays that can pass through our line of sight, like this. Another type of X-ray pulsar is when a neutron star is in a binary system and it pulls matter from its companion, forming an accretion disk. The matter coming off its partner circles around the neutron star, gets heated, and releases X-rays. That's why this is called an accretion-powered X-ray pulsar. Here you can see a red giant that is encroached upon the Roche lobe of this neutron star, bleeding off some of its mass, which then leads to an X-ray pulsar if the beam is headed our way. So talking about other exotic forms of radiation. Oh, this is for a different symposium, isn't it? What I wanted to talk about was not lions and tigers and bears, but quasars, blazars, and bears. Strange quarks, that is. Strange quark stars might represent something in between a neutron star and a black hole. It's believed that neutron stars right now are the most compact form of matter. But neutron stars could be compressed even further, perhaps, into quark stars. And in those quark stars, the up and down quarks might reconfigure into some strange quark components. And this represents a lower energy state, releases energy, and could account for some of the more unusual, long-lasting supernova. So blazars, in this artistic representation, it's a little bit unrealistic and a little overly pessimistic because these blazars are galactic nuclei that are millions or perhaps billions of light years away from us. And the relativistic beaming of the jets make the blazars appear more intense and brighter than they really are. In any case, they are sources of high energy gamma rays, as are quasars. Quasars are the most luminous of all active galactic nuclei, and they're powered by supermassive black holes, ranging up to tens of billions of solar masses and having a very large hot accretion disk that generates the electromagnetic radiation. Here's a photograph from the Chandra X-ray satellite of a quasar with a highly luminous X-ray jet. Here's an artistic rendering of a quasar blasting out some X-rays. Since we're at Fermilab Ask a Scientist, everybody knows what a tevatron is, but what's a pevatron? Pevatron is a nickname given to cosmic ray factories that accelerate particles to PeV energies. PeV, that's some pretty intense radiation. Really, what could generate radiation that energetic? Well, it turns out that some of these galactic cosmic rays have truly astronomical energies, not just in the GeV or TeV range, but in the PeV range or higher, some of them in the EeV range. And what could be producing that? What's this, the Crab Nebula? No. Seriously, the Crab Nebula is a pevatron? Well, it does make sense. The Crab Nebula is the brightest gamma ray source in the sky, and it does contain a pulsar that excites the gas around it and emits energetic photons. Recently, just in the last year, gamma rays from the Crab Nebula were detected with energies up to 1.1 PeV. Another very exciting exotic source of radiation are the Fermi Bubbles. These emanate from a supermassive black hole in the center of our galaxy, Sagittarius A star, and that supermassive black hole spawns relativistic jets. Powerful magnetic fields accelerate charged particles through these jets, resulting in the so-called Fermi Bubbles. These Fermi Bubbles are huge bubbles of plasma that are glowing in X-rays and gamma rays, and it's believed that as recently as 2 million years ago, an explosive outburst from Sagittarius A star led to these Fermi Bubbles. So is there any evidence for all this stuff that I'm talking about? Making a nice story up here, but is it true? Well, we know that carbon-14 exists, and you can use it for dating biological substances. Tritium is a form of hydrogen that is radioactive and comes from outer space, as does beryllium-10 and some of these other cosmogenic radionuclides. Tritium is produced primarily through interaction of cosmic rays and our atmosphere. And in fact, 4 million curies of it is deposited on Earth every year. And what do we use it for? Well, when the lights go out and they really go out, meaning no generators or nothing, how do you think you're going to find that exit sign? Sometimes it's thanks to the tritium. So cosmogenic nuclides don't have to be radioactive. In fact, the so-called Libib elements, lithium, beryllium, and boron, were not made in the Big Bang. They weren't made in stars either, thanks to the so-called beryllium barrier to nucleosynthesis. So they're rare in the solar system, but they're common in cosmic rays. And they are the source of, that's what emeralds are made from. Beryllium is the principal ingredient in beryl, beryllium aluminum silicate, one of my favorite minerals. And so next time you look at your emerald ring, don't forget that it was a product of outer space. Same thing holds for lithium. Some of it was made in the Big Bang, but were these lithium batteries made in Japan, made in China, made in the United States? Well, don't forget they were really made in outer space. Boron. I won't talk too much about boron, except that it's something that I might be using in my own research for boron neutron capture therapy as a new exciting form of cancer treatment, wherein boron 10 captures a neutron, undergoes fission, releases the energy, potentially destroying the tumor. So, is there radioactivity in the world around us, and how dangerous is that radioactivity? It depends on the source and delivery system of the radioactivity, I suppose. He's dangerous, but what about this guy? Well, he could be dangerous too, right? That looks like one big bad banana. Well, he is radioactive after all. Yes, bananas are radioactive, and so are these Brazil nuts. You ever wonder why Godzilla's back glows in the dark, by the way? It's because of his radioactivity. It's Cherenkov radiation. Cherenkov radiation is when charged particles are moving faster than the speed of light in the medium they're traveling through. They emit this blue light that's called the Cherenkov radiation. Here it is in a human patient that we're treating with radiation therapy. The math behind it is fascinating, but I won't go into it in any detail. But I'll say that Brazil nuts are radioactive because they accumulate radium. Lima beans, bananas, avocados are rich in potassium-40, as are all fruits and vegetables. So before you overdo it, though, be careful. A dose of 100 million bananas at once usually causes death within 2 weeks. So be careful. Potassium-40, carbon-14 are sources of radiation that we get from our food. But before you get afraid of eating all those bananas and Brazil nuts and orange juice, don't forget that one double hamburger a day also gives you some radiation. You just can't get away from it. But do be careful. Eating 2 cheeseburgers a day might give you more health problems than the radiation itself. And potassium-40 means that if you're sitting next to somebody, that person is blasting you with 4,900 decays per second. So people are radioactive, cats are radioactive, dogs are radioactive, and we can't get away from it. Potassium-40 is the most abundant of the terrestrial radionuclide sources, and it was present in much greater numbers in the distant past. Here are some of the primordial radionuclide decay chains. One of them is missing. It's the Neptunian chain. It's extinct already. The bottom line is that Earth was far more radioactive in the distant past, and that means our biosphere is no stranger to ionizing radiation. Can probably handle it. But let's take a look at some extreme situations in the final minute or two. Geomagnetic reversals can occur where the North Pole and the South Pole might sporadically change place. During these periods, the magnetic field strength is compromised. Our magnetosphere would be less protective. Right now, we're adequately shielded. But what happens when the North Pole and South Pole switch. During that period of collapse, we might not have shields. And what will happen then? Could be a problem. What if the shields of the sun were down too, where the heliosphere was temporarily inactive during a grand solar minimum, for instance? Well, we know that this occurred with the Maunder minimum, and it might affect the climate, but what if both of them were going on at the same time? Could it be a problem? Probably not. Probably has happened many, many times over Earth's 4.6 billion year lifespan. But could it spur on biological evolution by providing more raw material for natural selection to work with? Interesting idea. But could there be a more hazardous coincidence? What if we had a geomagnetic reversal, a grand solar minimum, and a supernova went off at the same time? That triple header could be hazardous, right? Would that be a perfect storm that could spell trouble for us? What if, in addition to that, we had geomagnetic reversal, solar minimum, and a northern excursion? What do I mean by a northern excursion? There's one more shield that I haven't talked about. That's the galactic shield. So northern excursions are not going to the North Pole, but north of the galactic plane. The galaxy rotates every 225 million years or so, goes around and around, but we go around it in a sinusoidal pattern. And when we are north of the galactic plane, we might be exposed to more radiation than normal. Folks from the University of Kansas and Brian Thomas of Washburn University have led the charge in this area. Dr. Thomas has been very helpful to me for putting this presentation together. So what happens if we leave the shielding of our galactic disk? Will we get blasted with more cosmic rays? We would. And what if we had a geomagnetic reversal, a grand solar minimum, a northern excursion, and a supernova goes off at the same time? That would be pretty intense dose of radiation. We know what that's going to cause. So is it a problem? I think it's not, as long as you're not going to get them too mad. But what if there were one more coincidence here? And could this be the straw that breaks the camel's back? Well, we all know that radiation causes mutations, but what does that even mean? So I think I'll stop here and entertain any questions if you have any.
Well, thanks for a great presentation, Jim. We will take some questions. Do GRB destroy interstellar medium?
I don't think the GRB destroys the interstellar medium. When the gamma rays hit the interstellar medium, it produces, when the plasma hits the interstellar medium, it produces radiation that we can see. The plasma, upon striking the interstellar medium, releases the radiation that we see in the form of an afterglow, but I guess it does change the composition of the interstellar medium a little bit, but it doesn't destroy it, it contributes to it.
Okay, and we have a couple of questions about ozone. Does the lack of ozone from climate change affect our chances of blocking out radiation?
Interesting question. The climate change issue is probably not directly affecting our ozone layer, but chlorofluorocarbons certainly have destroyed a fraction of our protective ozone layer. Interestingly, Thomas Midgley Jr. was the inventor of chlorofluorocarbons and leaded gasoline. And the chlorofluorocarbons did a number on our ozone layer. And it's making a slow comeback, but it is probably not as intense as it once was centuries ago. And there is that ozone hole over the Antarctic area. But if our ozone layer were to be attenuated further by chlorofluorocarbons or something else, and a gamma ray burst headed our way, that could mean that the little ozone we have would be diminished even faster. So, in a way.
Yeah. And if ozone gets damaged, how long would it take to heal, and what does that mean for Earth? Like, what would it cause? Like, would it cause extreme heat that could lead to extinction?
So it probably would not cause extreme heat, but since ozone is the primary means of attenuating the more damaging UVC and UVB energetic ultraviolet, we could be at risk for biospheric damage that way. The ozone doesn't have much to do with the temperature or greenhouse effect, but it is the primary shield of the ultraviolet. And if it were destroyed, it might take quite a while to be replenished, depending on how extensive the destruction is. After all, it is produced photochemically from oxygen, molecular oxygen, O2. If plant life, the phytoplankton, for instance, were greatly diminished, well, then the source of O2 through photosynthesis is correspondingly diminished. And it could take, I would estimate, centuries to restore balance again.
And we have two more questions. If we want to put people on Mars, how can we protect them against cosmic radiation?
I think that's a great question. I talked about how well shielded we are here thanks to our geomagnetic shielding, and I presented some unusual, bizarre, worst case scenarios where the shields are down and all that. But Earth is pretty well protected by the geomagnetic shield. Also, we're pretty well protected by the atmosphere. Not true on Mars, where neither are very effective forms of shielding. So this type of research is important because astronauts and future colonizers would be at risk for dramatic events. Now, there is some baseline radiation as we travel to and from Mars. As soon as we leave the protective magnetosphere and atmosphere, we're at the mercy of solar wind, solar particle events, and things of that sort. And shielding of spacecrafts and abodes on Mars would have to be very strongly considered. And biological protection through the forms of mitigators might be more important too. So being aware of when a blast of radiation could be coming our way would be very helpful. So having systems that could serve as early warnings for a solar particle event are feasible and could be helpful. Might not have the same kind of benefit for something coming from the other direction. If you have the early warning, you could seek shielding in a man-made or Martian-made underground shielding shelter, or you could perhaps prepare by taking so-called radiation mitigators, things that could be scavengers of free radicals, things that might protect you against so-called acute radiation syndrome. This is another area of active research.
We have time for one more question. How long does it take a CME to reach Earth? And has there been any improved protection on Earth from Carrington level events?
So the photons from the sun reach traverse the 93 million mile distance in about 8 minutes. But the particles coming from solar flares, CMEs, might take considerably longer. We might have hours, maybe a day or so, to prepare for it, depending on just how energetic and how fast those charged particles are coming at us. Like we say, oh, it's going 1,000,000 miles an hour. That's actually kind of slow for solar particles, but it would mean that we have 93 hours to prepare for the blast. So it varies as a function of energy of the CME, and well, what was the rest of the question?
And has there been any improved protection on Earth from Carrington level events since that last one?
Well, maybe not. So I think it's helpful to be aware of this and just how vulnerable we are, so that we can start to take some protective action. Because right now, I'm not convinced that we're prepared.
Okay, well, great. Thanks, Jim. We'll wrap things up today with a short drone video of the Fermi Lab site. We're now inside Wilson Hall, named after our first director, Robert Wilson. At 16 stories high, it's the central building on site. It contains offices, labs, experiment control centers, and an art gallery. This atrium is one of the largest in the country. The grassy area you see out the window in front of the building contains the Fermilab logo, designed by Robert Wilson and artist Angela Gonzalez, our 11th hired employee. It shows two of the electromagnets we use to control the particle beams. The parallel lines represent dipole magnets, and the curved lines represent quadrupole magnets. The flags you see on the left represent the countries that participate in the experiments at Fermilab. And the two buildings you see there off to the left, I'll talk about a little bit more in just a minute. Beyond those buildings to the left and over Wilson Hall is our main ring, which I will also give you some more information about. This pond is one of several on site, and through an elaborate pumping system, the water is used to dissipate heat generated by the powerful electromagnets. This building under construction is the Integrated Engineering Research Center. It will be an office space for our engineering specialists to work more closely with each other and the personnel in Wilson Hall. Inside the canal is the main ring, which at 4 miles in circumference is the largest accelerator ring on site and is where the Tevatron is located. The white building, also under construction, is PIP2 for Proton Improvement Plan 2. It will replace the existing linear accelerator and be the foremost facility in the world for particle physics research using intense beams. To the left of the building, inside the main ring, you see the first prairie restoration site on campus. About 1/6 of our 6,800 acres has been restored to tallgrass prairie. The square concrete building at the bottom left is the start of our linear accelerator, or LINAC. The beam extends out 500 feet beneath the grassy berm with the white top. At the end of LINAC, particles are transferred into the circular booster accelerator that you see around the pond. Particles circle the ring 20,000 times a second and are accelerated to 98% the speed of light. The building in the pond is a water treatment plant that supplies deionized cooling water for the magnets in the accelerators. These three buildings house our on-site neutrino experiments. And beyond the buildings, you can see more of our restored prairie. The buildings on the right are our industrial complex where we build and test equipment such as magnets and radio frequency cavities that are used here and at other laboratories. The sculpture you see in the left there is named Tractitious and is one of several on site created by Robert Wilson, who was also an amateur artist and welder. It was made from leftover stainless steel cryostat tubes from the Tevatron construction. In the distance, you can see distinctive power poles designed by Robert Wilson and resemble the Greek letter pi. This building is the Illinois Accelerator Research Center, where Fermilab scientists collaborate with other scientists and private industry people to research and develop accelerator science for use in public products and services, things such as stronger tires for your cars and water treatment facilities. This is Fermilab Village, sitting on land that was previously owned by farmers. It now contains, among other things, temporary housing, a gym, and a pub. Beyond the village, you can see some of the crop fields that are leased to local farmers. We're pleased to share that the Fermilab outdoor spaces and the Letterman Science Center are now open to the public. Information regarding site access is available at fnal.gov. We are currently in the planning stages for in-person events and tours. Stay tuned to ed.fnal.gov for updates or follow us on social media at FermilabEd. So stop by, visit the Bison, and check out the new interactive exhibits to learn more about our science at the Letterman Science Center. The building is open from 8 a.m. to 5 p.m. Monday through Friday and 9 a.m. to 3 p.m. on Saturdays. And for those of you joining us from a distance, don't worry, we will continue offering virtual programming so you can join future Ask a Scientist sessions from home. Since 1969, the lab has been home to a herd of bison. Robert Wilson brought the bison here to serve as a symbol of the history of the prairie frontier and Fermilab's pioneering research at the frontier of particle physics. The herd numbers around 30 and around 15 calves. The light brown animals are born every year. The female cows weigh on average around 1,100 pounds and the male bulls weigh up to 2,000 pounds. The herd is cared for by an on-staff herdsman, and these huge animals can run at speeds up to 35 miles an hour and jump a 4-foot fence. The American bison nearly went extinct in the 19th century, but thanks to conservation efforts, it is no longer an endangered species, and it is now our national mammal. You can observe Fermilab's bison herd with our bison camp, and we maybe can get a link to that in the chat. If not, you can find it on our website, fnal.com. Our next event is on May 15 and will be a virtual tour of the Fermilab site, followed by a panel discussion with scientists, engineers, and technicians to answer all of your Fermilab science questions. An email will be sent out to register for that event soon. My thanks to you, Jim Welsh, for your wonderful presentation, and to our education program leader at Fermilab, Amanda Early, for organizing this event and for being our Zoom guru. And thanks to you all for joining us here today. See you next time for Ask a Scientist.